Welcome everyone, again Matteo 𝘁cie from Politecnico di Milano, and I will continue these second lectures on neural architecture search. In the previous lecture, we have introduced the idea of developing an algorithm which will find the optimal architecture for a neural network solving a vision task. Today, we will enter into the detail of the anatomy of this kind of algorithm, which is called neural architecture search. This lecture is provided within the framework of the AI-SPRINT project. So, neural architecture search is a technique within the field of machine learning that automates the process of designing and discovering optimal neural networks for a given task. And this is an example of automatic model design. The anatomy of the typical neural architecture search system is divided in a few blocks. We have a search space, which is the space where we will search for the best model, a search strategy to search this space, to explore this space, and a performance estimation strategy, which means a way to evaluate whether one of the algorithms that has been selected by the search strategy is good or not. So you can imagine the search space as the set of all possible models. The search strategy is the criterion for which we select one specific architecture from this set, and we provide this specific architecture for evaluation. The performance evaluation strategy will return the performance of the model. Now, the search space, as I already introduced, is providing you all the possible network that a given algorithm can find. Depending on how you structure this space, you might find one specific architecture or not. The search strategy is the way we pick models from this space. We call it exploring the search space for the optimal architecture. Finally, the performance evaluation strategy. We would like to provide an evaluation of the architecture, and we will provide this evaluation in the most efficient way. One of the first work on neural architecture search was presented by Zoff and Lee in 2017 as part of their work at Google Research. And they used the reinforcement learning algorithm to perform this task. The goal was to search for the whole neural network architecture for a given task. And to do that, they decided to structure the search space as a set of multi-layer network. Each of these layers was defined in terms of number of filters, filter height, filter width, stride height, stride width, and number of filters again. So you see that the network is a concatenation of layers, all of them having the same shape. The approach that was used in that case was using a reinforcement learning controller. So the controller proposed a new architecture for evaluation, and this new architecture is then trained, evaluated, and by the quality of this network, the controller is improved. This controller, in this original work, was implemented as a recurrent neural network, which was generating a sequence of tokens of variable length, which were the size of the filter, the width of the filter, the stride, and so on, I was talking before. So the algorithm that was used to train this controller is called reinforce. This algorithm assumed that the controller has an action space. An action space is the list of tokens for the definition of the network that is predicted by the controller. The controller will predict a sequence of tokens a sequence of actions in the reinforcement learning terminology which describe the child network. At this point, the network is trained, is evaluated, and the result of this evaluation is called reward. The reward is how good was the network generated by the controller. Once we have this index of quality, this reward, the controller is optimized. Is optimized by maximization the expected reward. It means that we want to find the controller which is able to generate chills, to generate cells, to generate network with a very high accuracy. What does the controller do is generating examples of convolutional network. As I said, it generates a sequence of tokens, and these tokens they represent the number of filter, the filter height, the filter width, the stride height, the stride width, the number of filter again. Each prediction, in the sense that whether we choose a certain number of filter or height, is made by a softmax classifier. The score will be used to improve the controller. With respect to the basic model, which just uses layers one after the other, the controller can also add skip connection. These skip connection improve the quality of the classifier. This model was presented in 2017, and the result it achieved were quite impressive. The accuracy that this model was able to obtain was able to compete with the best human being design architecture. For instance, in this case, you see some examples with an error rate on the bottom right, which is very close to the error rate of human design network. What is important is that on average, the network proposed by the neural architecture search were having human-like performance, but way loss parameters. On the right, you see one of the examples of the network. You can recognize the structure with the sequence of blocks and the shortcut connection generated by the neural architecture search algorithm. The cost of training this model is the cost of testing 12,000 architectures from scratch. To do this, the authors they used something like 22,000 GPU days, and this means that unless you are Google or you have a similar computational power, this process is not practical, not scalable. Within the framework of AI-SPRINT, we would like to improve, to speed up the design of neural network architecture by taking into account also the cost of doing that. But this was the original idea. This was an algorithm proposed in 2017. In the following year, different ideas were introduced to speed up the process and to reduce the cost of training. Another example proposed by the same authors and inspired by the idea of some network in repeating block is called NASNet. In NASNet, the difference with respect to the previous network architecture search that I have presented is to use new blocks. These blocks are made of cells, and these cells they have different operations, multiple operations. The neural architecture search, what it does is to predict these single cells, and then the final model is obtained by concatenating multiple of these cells. So, for instance, the NASNet search space is composed by two network composing cell. Normal cells, for which the input and the output feature maps have the same dimension, for instance, like with convolutional layers, and reduction cells, for which the output feature map has its width and height reduced by half, like pooling layers in standard convolutional neural network. By combining these cells, we can build blocks like the one in the pictures, and by concatenating normal cell, reduction cells, normal cell, reduction cell for several times, we can generate networks which are quite good and can be even be portably exchanged between one dataset and the other. For instance, in the work of Zoff and the other colleagues of 2018, a model was trained on CIFAR10, which is a rather simple dataset, and once the cell was trained on this model, it was ported to a more complex dataset like ImageNet that we have seen before. So once we have a cell, what we can do, we can build new network by combining this cell. How do we build a cell? Well, according to the NASNet, we build each cell by using B blocks. It was 5 in the original paper, where each block contains 5 possible steps with 5 different softmax classifiers corresponding to discrete selection of the elements. Here you see some example. One of these is, for instance, a convolution added to the identity of a block. What is the advantage of the NASNet? Well, since you don't have to generate the entire network, but you just generate one cell and you repeat it multiple times, the search space is quite reduced. You can reduce the search space. It means that you can speed up the training. This is an example. The idea of the original paper of NAS by Zoff and Lee was to use a global network with a reinforced and a total cost of 22,000 GPU days. By introducing the idea of a cell-based approach, we can shrink down this cost to 2,000 GPU days with the same error, if not lower. After this, new ideas to improve the process have raised. One of these is PNAS. PNAS, which stands for Progressive NAS, uses the same idea of cell-based exploration, search space made of cells, but it explores this search space in a progressive search. So it will start from very simple model, and then one after the other will increase the complexity of the model. It uses a sequential model-based Bayesian optimization instead of reinforcement learning, and this helps in reducing the complexity as well. PNAS, Progressive NAS, make use of the same space of NASNet with the 5 element blocks in forming a cell, but the only difference is that instead of setting the number of blocks to a fixed number, it starts with a single block and then increases its complexity. Another important step in the PNAS strategy is not to evaluate all the network, but to use a surrogate model to predict the quality of a network. By doing this, it means that we don't have to train and evaluate each new candidate architecture or candidate cell. We predict its score, and this is way faster than testing and training the new architecture. And this is clearly visible by the comparison of time. Now, from 22,000 GPU days of NAS, we move to 2,000 GPU days of NASNet, and then to 225 days of training with PNAS. The two elements that have made this possible are the search base space based on cell and the idea of a progressive structure. Now, more recently, and this is one of the AI-SPRINT project results, we have proposed an extension of PNAS which tries to leverage a multi-objective search. Now, we don't just search the most accurate network, but we try also to find the most accurate network which is fast to train. This means that now we have a predictor for accuracy, like with the classical PNAS, but also a predictor for training time. By doing this, we are able to find faster network in training, but we are also able to find what is called a Pareto-Optimal solution. What does it mean? We find a search of models that we present to the design with different characteristics in terms of complexity and accuracy, and the designer is able to choose among these. This closes the second part of my lecture on neural architecture search, and we will complete this with new models that have been recently proposed.